Hi, my name is Kucherenko and I'm going to present our paper about the GENEA challenge, the first ever gesture generation challenge. This challenge was focused on generating speech-driven gesticulation for an avatar given a dataset of human speech and movement. If you could remember only two things from this presentation, they are appearing on this slide. We run the first ever gesture generation challenge and all the data is openly available. First of all, I would like to clarify the importance of hand gestures. Nothing does it better than this video.
Fammi la destra però, punto e basta.
A te ti fa male la testa?
Non a me,
Mm.
perché te mi fammi la testa a me.
I guess many of you who don't speak Italian could still understand what she was talking about. Researchers have been working on the problem of gesture generation for several decades. Early systems were mainly rule-based, while modern systems are usually data-driven. The field of gesture generation is not moving as fast as it could because there is no benchmarking culture in the field, and those who do compare with the previous work usually do not do it consistently. Everyone evaluates systems in their own way. How do people in the field evaluate the gesture generation models objectively? Many of us don't. Some people use canonical correlation analysis, others motion statistics, such as velocity and acceleration distributions. Recently, Frecce distance was brought to the field. Some probabilistic models can be evaluated by directly measuring the data likelihood. Some people use various distances to the ground truth, such as mean square error, but that should be avoided, since there is no single correct gesture for a given speech. Benchmarking has accelerated development in several other fields, such as speech synthesis, machine learning, and others. And it should also speed up progress in gesture generation. We felt like somebody needed to do it, and hence we run the world's first gesture generation challenge. All the teams participating in the challenge received the same dataset, which was kindly provided by Eva Förster and Rachel McDonnell. The dataset contains around 4 hours of speech and 3D motion. On top of the original dataset, we annotated the speech audio with time-aligned transcriptions. The resulting GENEA challenge dataset is now publicly available in the same repository as the original dream-to-speech gesture data. Here you can see an example clip from the dataset.
It's not like this. I won't stand for this any longer. I'm going to start a revolution. And
All challenge participants received synchronized audio, text, and motions in the same format. The gestures from the participants were rendered onto exactly the same avatar and compared in a joint evaluation. So nothing except the gesture generation systems differed between entries. We have developed and validated a new evaluation interface called HemVib, which enables evaluating several videos at once. Study participants watch videos one by one and give them rating between 0 and 100, corresponding to 5 anchors: bad, poor, fair, good, and excellent. Let me tell you some numbers from the challenge. We had 15 registrations. This resulted in 5 submissions and 2 open repositories of code from challenge systems. Luckily, those 2 correspond to the strongest systems. In the challenge, we included several top lines and baselines. I will now briefly describe the 2 synthetic baselines, which were based on previous papers in the field with open code, and 2 top lines, which were based on natural motion capture from the database. Our first baseline was an audio-only baseline, based on the work which appeared at IVA 2019. The model is based on neural networks and consists of 2 steps. First, it learns a lower dimensional representation of human motion using a denoising-encoded neural network. Second, it trained an encoder network to map from speech to a corresponding motion with reduced dimensionality. At the test time, the speech encoder and the motion decoder networks were combined. This model was trained on the challenge dataset, but with some changes from the original implementation. For example, joint rotation values were synthesized instead of joint positions, and smoothing was applied using a Savitsky-Golay filter. The hyperparameters were also tuned. Our second baseline was a text-only baseline based on the work by Youngwoo Yoon et al., which appeared at ICAR 2019. The model was based on neural networks and consists of 2 parts. First, an encoder part, which has a speech text as input. A Latin representation of that is brought to the decoder. The decoder then generates motion based on the Latin representation of the text it received from the input. The model was adapted to synthesize joint rotation instead of joint positions, and the word embeddings made use of pre-trained fast text instead of glove. Next to these two baseline models, we also included the ground truth and mismatch gesticulation. First, let's watch the ground truth motion.
But the thing is that if you've actually like fought people, if you've actually like done stuff like Thai kickboxing or things like that, getting kicked or kneed by somebody, you know what that.
Mismatched in this case means that the gesticulation displayed does not align with audio and was taken from another point in time from the motion capture database.
But the thing is that if you've actually like fought people, if you've actually like done stuff like Thai kickboxing or things like that, getting kicked or kneed by somebody, you know what that.
This gives a condition with high quality motion, but that has no relation to the current speech. Note that mismatch motion looks very natural. We will come back to that. We set up two crowdsourced user studies for subjective evaluation of the gestures produced by the teams that participated in the challenge. In each user study, a total of up to 8 stimuli per page were presented for evaluation. Only subjects who passed all our attention checks were included in the analysis. This gave 125 participants for each of the two studies. The first study asked, how human-like does the gesture motion appear? This question tried to investigate the quality of the motion while ignoring the link between motion and speech. For this reason, the audio track was omitted from these video stimuli. The second study asked, how appropriate are the gestures for the speech? This was intended to investigate the perceived link between motion and speech, and raters were asked to ignore motion quality as much as possible. We had our natural motion as a condition N, mismatched, condition M, audio baseline, BA, text baseline, BT, and the 5 entries from the participating team, SA to SE. Let's get to the results of the challenge. This box plot shows the results from a human likeness evaluation with conditions ordered by highest median rating. The boxes may look quite wide since there is a lot of variation in the ratings, but the 99% confidence intervals for the true median in red and mean in yellow are actually quite narrow. In particular, we see a substantial gap between natural motion on the left and other synthetic motion to the right of it. Here is a similar box plot, but for how appropriate the motion was for the speech. There remains a large gap between natural and other systems, but we can see that the order of the systems differ compared to the study of human likeness. Interestingly, the mismatch condition M had the best sample median rating aside from N, despite the fact that it was completely independent of the input speech. We think that this is because it's difficult for raters to separate motion quality from appropriateness, and also because of the data used, where the speaker is constantly both speaking and gesturing. If the speaker would have intervals of not speaking or gesturing, mismatch would be more obvious. With this work, we follow the open science principle. All the motions and videos, code for visualization and evaluation, user study results, and system description papers are publicly available. The QR code in the corner here leads to a page with all this data. The data can, for instance, be used for future benchmarking or for research into human perception and new objective evaluation measures. So what have we learned about the state of gesture generation? The technologies are improving. The gap to natural motion remains large. And different systems were good at different things in terms of motion quality or appropriateness for the speech. What have we learned about gesture generation evaluation? Our evaluation interface works quite well. Established objective metrics are not representative of perceptual quality. It's difficult to evaluate appropriateness well. What have we learned about challenges like ours? Challenges address unmet need in the gesture generation community. Good datasets are rare and often smaller than we would like. Active participation of the community is essential for challenge success. Thank you for your time. We are happy to answer your questions now.